Hello, everyone. Welcome all to this space. I'm very happy to be here today sharing with you my passion for complexity science. And so today what we're going to do is to look at cities as living organisms. So the whole idea that we're going to do today is to see how cities are places for change and transformation, and how these transformations and these changes give rise to interactions, to emergent patterns that can be also found in nature. So these emergent patterns that can be found in nature, we know how to study them. We have the whole set of tools from complexity science, and what we're going to see today is, can we borrow some of these tools in order to get a better understanding of cities? And moreover, in order to get some insights that maybe we wouldn't have been able to know if we didn't think about them in this way. So in order to get started, let us look at cities' utopias, right? So this idea of what is the ideal city. So the first set of utopias that we're going to explore is Thomas More's utopia, who is actually the person who coined this word. And so in his frame of mind, what he wanted is this idealized society in which he would put then a structure, some sort of political structure and organization, so that everything will work perfectly, in some sort of pseudo-egalitarian type of framework. And within that, one can think about changes that might occur and so forth, but it was all very well contained and thought with respect to how that will impact division of labor and so forth. And one can think about this sort of abstraction as something that just stays there lying about, but actually Vasco de Quiroga used it in Mexico in 1535 in order to argue that actually people shouldn't be enslaved. You know, Carlos V, Charles V of Spain wanted to slave the indigenous population, and he used this argument, taking all of the insights from Thomas More's in order to say no to this kind of thing. And in addition, he also took this idea of how the society should be organized to try how it would work in Mexico. Another type of utopia that we can think about is the utopia put forward, which is a bit different of Francis Bacon. So we can think about the utopia of Thomas More as some sort of governance, an organization of the whole society. But then you have Sir Francis Bacon proposing something a bit different, something that relates to a utopia of how you will relate to your environment. So how could people have access to knowledge? So how could people have access to this very important resource that would allow this transformation? And actually, he was one of the ones putting forward a scientific method in order to achieve this type of thing. And so, of course, when one thinks about these utopias, it's like, okay, so these are the utopias, but can there really be something that is tangible? Are people really using this in order to construct something? And we have some examples. For example, the Venetian Republic in the 16th century constructed this place that is called Palma Nova. I don't know whether anybody has been in this place. And so the idea of this place is not only a beautiful configuration in which it's a fortification because it was right in the middle of wars and so forth. So you needed to construct a fort that would really support all the soldiers inside in order not to allow people to get in. But in addition to that, also Thomas More's idea of how the society will be operated in these egalitarian terms was put forward. Nevertheless, given its situation in which you have a place that is being attacked all the time, people didn't want to live there, and in the end it was the soldiers that lived there where they put this type of organization. So of course it's difficult to gauge this type of experiment. And something that is normally not seen in cities around the world is a city that was created like that, and then the shape stay the same. So you can all go and visit this place and it looks exactly the same. But of course, don't be fooled that the shape hasn't changed, because the way people will be behaving, the way all the things that are in the city and make the city live and make the city have flows of individuals and so forth, that has changed. So the form stays the same, but the function has changed. And thinking about all these type of utopias, so we have governance, a utopia that thinks about a top-down approach of how the individuals will be living. You have another utopia, which is about exploration of your environment, your relationship with the environment, access to resources. And then you have another one, which relates to the individual perspective. So one of those is depicted here in Remedios Varo's painting in which this type of utopia relates to the spiritual and alchemist principles. And this painting actually is based on this other work by de Gusen, that actually what he had was a labyrinth. So the whole idea of the individual is how the individual will enter this labyrinth. He will go into a transformation based on knowledge, and in order not to get lost, he needed really to use all that and exit the labyrinth. So it's a transformation of the individual. So all of this to say, we have in the utopias of cities and this idea of top-down approach of governance, we have how the individuals, the flows that might be created when you think about how you will be accessing resources, and the role of the individual, how this individual connects to that, whether he's part of a community or not, for example. So when we look at cities around the world, what we see is cities that are really different. So on the one hand, we have cities that are coastal cities. On the other hand, we have cities that are in the desert. We have European cities very strongly connected to their history. We have cities that are really heterogeneous in the way they are organized. And we have very modern cities. So all of these cities, when we look at them, very, very different to what we saw with Palma Nova, these cities are the outcome of change. These cities are not cities that somebody thought about this city, and there you have your city, and it will function like that forever. These type of cities are cities that are the outcome of the collective. Okay, so there isn't a single individual, and this is very important. Even though you have planning and you have all these sort of things, it is a set of collective decisions that give rise to the way these cities are going to function and the way these cities are going to look like. So, and they're constantly changing and evolving. And we have these utopias, and we think about one system, we think about another one, but nobody can predict how these cities are going to look like in the future. What sort of new technologies are going to come in order to change the way we're going to relate from one point to the other. We're going to relate to individuals. So all in all, what you have is a set of tensions. Tensions with respect to regulatory systems, top-down approaches, and the changes in the needs of people that might come up as well with respect to flows of individuals, new individuals coming into these cities. Moreover, when we look at our world, we have very different landscapes. We have very different access to resources. We don't have a unique set of way of how things are defined to see how this city is going to function, and you're going to be able to access these resources, and you are going to be able to organize your society. So taking that into consideration, we observe that different cultures have emerged, different types of individuals, and I recommend to you to look at the pictures of this Alexander Kimushin. He has a collection of pictures of people from all over the world representing all these different cultures. But this is who we are. We are a set of very different cultures with very different access to resources, very different landscapes, very different types of tensions. And in addition, we also have very different historical trajectories. So for example, if we look at the beginning of the cities, we look at a city like this one, Uruk. The first reaction when you see this is like, why is this city in the middle of the desert? Who would build a city there? And of course, this didn't look like a desert when this city was built. There were resources there, and this is why the city was built there. But of course, now you have climate. You have the climate has changed, the environment has changed, and everything. And now it is desertic, and you don't have a city anymore. Another example is Tenochtitlan. So this is the city where I come from, and this is the city how it looked like back before the Spanish arrived and colonized Mexico. So this looked like a little Venice, right? And people will go in canoes and will be around and will be cultivating in this space. And if I tell you that nowadays the biggest problem of Mexico is water, when you look at this picture, it sounds crazy. How can it be a city that was created in the middle of a lake have problems of water? So if you look at Mexico, this is what happened. So this is how it used to look like, and this is how it looks nowadays. So all the water was drained, and now we have problems of water. And there are these beautiful animations created by Thomas Cole in order to show you how these cities look like back in the day in these 3D simulation kind of things. So any coincidence with the way these fractals are arranged in the table, you might see where it comes from. So this is how it looks like nowadays, okay? So this was the most important temple, and now you see that, of course, the cathedral was put right there where you have the most important temple in Mexico. Okay, so we've been talking about all these different cities, these different type of approaches to what is a utopia, and we have different histories, different environmental constraints, different cultures, different everything. So could we really find some sort of universal way to understand cities? Is there anything universal about cities, having said all this? Can we find some tool in order to say, look, it doesn't matter that you have sociopolitical histories that are different, it doesn't matter that you have a different culture, can you really come up with something that is the same everywhere, that is universal, that you can take your microscope and look at it in the same way for all of the cities? And of course, the answer is yes, otherwise I wouldn't be here telling you about all of this. So one of the answers, you might think about many different things. One of them is the morphology of the cities. So when we look at cities, why do we have cities? What is going on with respect to cities? So cities, the most important thing about cities is that it brings people together. There are cities of interactions. And not only the cities are places of interactions for individuals, they also need to be connected between them, because otherwise it wouldn't work. So if we think of cities as places of interaction, then one thinks, how can I measure these interactions in my system? Okay, so I don't know how people really are interacting, So how can I measure the temperature in the different areas, of my system? As a physicist, that's the way I will be looking at. One way to think about it is roads. Why roads? Because you see, a road is a place that is connecting two spaces. If these two spaces are important and this connection needs to continue, as the years go on, this road will remain. So there will be a positive feedback into this road. If the connection between these two spaces doesn't really matter, then this road will be erased. Okay? So this road gives you a proxy of these interactions that can be. And not only a proxy of the interactions that can be, a historical proxy of how, a footprint of how these interactions end up being there. And this can be seen in the Roman roads. So even nowadays, you have, because we're here in London, we have a lot of Roman roads that are very important ones. So all the 8 ones that are in that map over there are Roman roads. And in those roads, you can recognize them as the A10, or maybe I'm wrong, the name or one of those that goes to stands that are over these places. You can also know that in those places, in the oldest roads, in these Roman roads, you will have concentration of retail. Okay, so these will be roads of importance. And not only, of course, you will say there are not Roman roads everywhere. Of course not. So this is not the idea that you have universality in Roman roads, because of course this wouldn't be the case. What you have is a universality in the way cities are connected. So not only you have cities everywhere, but these cities have a very special pattern, and these cities are fractals. So we have sitting here among us the person that came up with the idea that these cities were fractal, Michael Batty. So he proposed this in 1994, and I think around the same time, Frank Hauser was also working on that, and he came up with this proposal. So the cities, you will look at them, and they all have very different configurations, but they all are fractals. So when you look at the cities in London, you look at things that look like that. So you wonder, the fractal that maybe you're more familiar with will be the Mandelbrot set, the one that you have on your right. And this other one looks a bit ugly, to be honest, when you think about fractals. So it's the way the relationship between the elements can be understood. So on the right-hand side, you have fractals that are mathematical fractals. They are called regular fractals. You construct them in a regular way. What you have on the other side, those are random fractals, like the ones you will find in nature, or the ones that we are creating. So, looking at these fractals, we live in landscapes that are like this one. So this picture was taken in Tenerife, so it is a volcanic landscape that if you zoom further, okay, so when you look at this one, it looks very similar. It looks very similar to the Mandelbrot set. So if you zoom even further into this landscape, then you see that the rock itself is also a fractal. The way the pores are organized within this rock, it's in a fractal structure as well. When you look at another type of landscape, for example, a forest, then you see that you have this thing that is called crown shyness. So you have all the trees that are growing, but the trees don't want to be touching each other. It's very nice for them to be interacting with the roots, but once they grow, they don't want to be touching each other. So doing that, they create these fractal patterns that are out of this crown shyness. So we have the forest that is a fractal. Once we zoom in into the forest, we see the tree. And the tree, the way the branches go out, this branching process is also a fractal. And when we zoom even further into this tree, we have a leaf. And this leaf has also this fractal structure. But not only that. In addition to a fractal structure, it has something else. It has a hierarchical organization. So when you look at the leaf, you will see that the veins are of different sizes. Okay, so straight away, you know that this leaf is organized in a hierarchical way. And this hierarchical organization plays a functional role. The size of these veins is very much going to tell you how much of transport of water can be done in one place as opposed to another one. Okay? And something very important, why does it look like that? Because of the environmental conditions. So if you were to take a fossil, for example, from a plant, and you were to look at the way the veins are organized, you wouldn't be able to tell what was, for example, the weather back in the day of the time of this fossil. So it contains all this information with respect to the functional way. So it's a fractal whose structure is telling you about the function. So back to our streets. If we look at our streets, we also see this type of hierarchical organization. Roads in which you can go faster, you can reach faster one place to another one, and so forth. So when you open your Google Maps or your OpenStreetMap, you have some sort of colors seeing what is the hierarchical structure of all of these streets. But what if you didn't have these colors and you wanted to navigate the space? How would you know, or you wanted to understand, what is the hierarchical structure of a system like this one? You could look at the amount of information that this system has. So you could look into how the flows will be connected between them and how the information will be traversing this system. And you can do that using Shannon's entropy. So this is one of the, I think I have only 2 equations. This is one of the equations showing you how, with mathematics, you have this subject and you just take it and you're able to then put all these colors and you're able to understand this hierarchical structure and how then this hierarchical structure is going to play a very important role in the functioning of the city. Okay, so this is the important thing. In the same way that you have your leaves that need to have this hierarchical structure, you will have also these other objects that will contain a structure that its information will be able to tell you something different about the system that maybe you didn't know before. So we went from the landscapes, from trees to leaves. Now let us go from cities to humans. So when we look at humans, we see that, for example, the eye is also fractal. When we look at our lungs are fractal, and if you turn around the lungs, you will see that it looks like a tree. So this is a very important morphology of the lung. In order to be able to capture all the oxygen that needs capturing, it needs to have this fractal structure. It needs to have this branching process in this way so that you're able to live. And if you want to go even further, you could see where there is more fractality among you. And so overall, one thinks, okay, so fractals, they all seem so different. Where do they come from? So how come that what you're saying now, Elsa, is that not only you're saying that I'm a fractal, yes, we're all fractals, but also at the same time, we are creating a fractal world without knowing that we're doing that, and also in a collective way. So it's not that a person comes and said, I'm going to put now a new street here in order for the fractal dimension to be better. All collectively do changes into our systems that we live in, into our cities, and then we produce these fractals. So where these fractals comes from? So when we look at fractals, of course, the person that needs to be in any slide is Benoit Mandelbrot. So how he came up with the fractals is because he wanted to describe the world. So Benoit said, okay, I want to describe the world. I have this amazing geometry that Euclid gave me. I have squares, I have circles, I have triangles, I have all these type of things. I want to describe this nature that I'm seeing it. How am I going to do that? Well, these circles and these squares and these triangles are not good enough. I need a different type of geometry that tells me about the roughness of this nature that I'm observing, because nature is not behaving in this Euclidean way. And so he came up with the word fractal coming from the idea of broken, okay? Not from the idea of a fraction. Sometimes people say this, but it's not from fraction, it's from broken. So when we look at fractals, we have this type of things, right? So on the one hand, we have trees and plants. And then on the other, we have things, for example, like a thunder. Or we have something like this one, that the first impression will be, this is a tree, but this is not a tree. This is rainwater erosion. So we have a few fractals here that we have shown, and you don't have a single process that gives rise to all of them, okay? Each fractal that you saw comes about from the interactions of the many different agents in a very different way, and tensions from the environment and so forth. So you don't have a unique process that gives rise to fractals. And as an example, I have here an experiment, which is electrodeposition of copper. So actually, this experiment, you can do it at home. You can Google all the things and create your own fractal at home. And this is what happens. So you have filament of copper, and then you have this solution of copper sulfide. You put some electricity, and this is how you end up with your fractal. So when you look at a fractal like this one, it's like, I've seen this fractal before, right? You've seen this fractal before. You have all seen this fractal before. In winter, you see it in snowflakes, you see it in many different type of places, but they're not creating with electricity, yes? So many different processes give rise to these amazing patterns. And when you look, for example, if you want to see, like, how could I construct a fractal? And I'm not quite there yet. What do you mean by fractals? How do they come about, and what are they? So let us create one from scratch, without electricity and without experiments and so forth. So you have a triangle. Then in the middle of all the different sizes of the triangle, you create another triangle, okay? So you create another triangle, and you have a hole now. So of course, the area of this triangle is less than the area of the triangle that I had before. And I have 3 triangles left. And I do the same to each of the triangle left. And I have 4 holes now, and I have more triangles. So the area of this one is even less than the one before. And I continue this operation, and I continue this operation, and you can see that this operation can be continued to infinity, okay? So this fractal is an object that is self-similar. It looks the same. If I take just one part, if I take just, for example, this one here, it looks exactly the same as the whole thing, Okay? So I can zoom in and zoom in and zoom in and zoom in and recover exactly the same pattern that I had at any point in my fractal. You can also create fractals, in a very nice computer way. And if you suffer from any type of dizziness, don't see the next video, although it might remind you of the raves when you were younger. So you can see how you can zoom in to the images and recover exactly the same pattern that you had before. So these are mathematical fractals. These are not the fractals that we're going to find in nature, because of course you will have a finite, they have to be finite. They cannot go to infinity in nature. You will end up with atoms, molecules, atoms. Of course, you cannot have an infinite fractal in nature. So we saw, okay, all of these patterns. So we have these fractals that you said also show this hierarchical structure. And these fractals show these hierarchical structures because they have some sort of heterogeneous interaction. So we saw in the leaves that some parts of the veins, you have more transport of water than other ones. So you don't have the same amount of interactions between A and B in all the types, in all the places in your fractals. So it is this heterogeneity that gives rise to this emergent behavior. And so when we look at our cities, for example, we saw, okay, one way to understand our streets with respect to all this hierarchical structure, but there is more to it into the function. What is its role? So how can I go beyond that and understand how my country, my cities are organized in terms of a hierarchical way? So one example, we can take an example from us again, from the way our brain works. So when we look at our brain is very modular. So our brain is organized in a hierarchical way such that you will have parts in your brain that are really, really connected within them. And then another part of the brain, so you have two modules that are really, really connected in each of those, but they also need to interact together. So you don't have the case in which each module is working on its own, and all of a sudden they're all connected at the same time. You will have a different way in which one part of the brain is going to be connected more to another one, and depending on the sort of things that you're going to be doing. So how can we understand the hierarchical structure of our brain in terms of these types of systems? So this is a paper that did this type of experiment that actually it was the inspiration for the rest of the stuff I'm going to show you in the talk today. So you have the patient, and then you give some stimulus. And then you record which part of the brain lit up. And you will see, I don't know whether you can see in this, I think you can see, it's very big, this screen. You will see a little red dot appearing in one over here, okay? So read it in this way instead of that one. So you have a little stimulus appearing, right? And one bit of the brain lights up. Then you increase the stimulus, and you have another bit of the brain that lights up, the green part, okay? And as you increase the stimulus, you see other ones appearing. But all of a sudden, there is a transition here. So you see here, I'm plotting which are the parts of the brain that lit up once I put this stimulus. So I put one stimulus, and I have this red bit. I continue to increase the stimulus, and here I have three areas of the brain, so I have three little dots, okay? The green, the orange, and the red one. And then in the next bit, the orange and the red merge together, okay? So you're not able to distinguish this modularity in the next, but then you have a new one that appears. Okay? So as you increase the stimulus, you start to see new areas of the brain that appear, and you start to see how they start to merge together. So overall, when you look at the tree that you obtain by observing your brain, this tree here, you observe this hierarchical structure of how your brain is operating with respect to this stimulus. how can I use this brain for my cities in order to be able to study my urban systems, right? So we were saying the idea is to take all this inspiration for nature in order to try to understand better. So when you think about cities, it comes to mind that you have like little modules that are in a country, and you have a high connectivity in these modules that are each of the cities, but they need to be interacting in order for the whole country to work. Because if the modules are each of their own and they're not interacting, you wouldn't have a functioning space. So we can study these cities in the same way as we study our brain. And so this is what we're going to do. So how do we do that? So we already gave a hint with respect to understanding our interactions in terms of our road network, okay? So because we don't know how to other than impose boundaries, administrative boundaries on the space, we really don't know how people are interacting. So cities are not cities if you don't have people in them interacting. The only way that you can really think about cities is the flows that the people create. So how can I then gaze into how this can be happening? So one way is to look at the proxies of how could people interact. How I'm going to do that? I'm going to say that things that are closer together, and this is very much Tobler's law of geography, you're going to assume that things that are closer together have a higher probability of interacting. So you don't know whether things are interacting, but you will assume that things that are closer together are going to have a higher probability of interaction. So I take my road network. For example, in this case, I have the city there, the map of the city from OpenStreetMap. So you can download any map for free from OpenStreetMap all over the world. And not only that, you can also input into the map. So for example, if you're from a city that is really small and don't have all the streets, you can go there and edit it and put a new street. Okay? And this is very much something that is done in emergency circumstances when you have tsunamis and these type of things, and you need people to get into these places. You have OpenStreetMap, to allow for people to be able to take satellite pictures and then input all the missing roads. So OpenStreetMap is quite complete. So we have these maps of streets, and we want to take these maps of streets as places of interaction. So we convert these maps to a network, and this is how the network looks like. So it's just dots that are connected by a street, okay? So basically, if you have something like this, it will transform into the network that you have on your left. So you have any roundabout will be just one node connecting to all the different streets. And so how are we going to use that in order to study our cities? So we have our road network, and we're going to say, okay, so closer things are going to be more connected. So we have our nodes, which are our points of intersections, and thus, if the distance within these nodes is smaller, it will be easier for the message to pass by, for the interaction to happen. So just imagine that you have your city and you want to pass a message, and you are only allowed to pass a message if you don't have to walk very much. So the message you will have here 4 communities that appear, okay, in red. I don't know whether you can see them. So you have 1, 2, 3, and 4. And all the rest of the nodes are going to stay disconnected. And as you allow for this message to be able to spread further into your system, you say, okay, maybe you can walk a bit more. Maybe you can shout a bit louder, for the message to propagate, or you can think about an infection, whether it can propagate in the space. Then you have 1, 2, 3, 4, but you see that there are new members in your communities that are able to interact. So as an example, if you had a network like this one, in which each of the numbers that are in there corresponds to the distance, then if I say I can only whisper a tiny bit in order for the message to pass, you see that the message wasn't loud enough to pass, okay? And so I will represent all the points of intersections at the bottom of my tree. because none of those were interacting. Then I say, okay, I'm going to increase the stimulus. So in the same way that we were increasing the stimulus in the brain, I'm going to allow for the message to pass, if the distance is at least 2. So when I do this, then I start to see some communities forming. I only have the one community that forms, and then I create my tree in this way. So you see in the second stage, at the beginning, you have all the leaves that are the nodes. In the next stage, you have a new community that forms with all of these 4 ones that is here in yellow, and the other ones remain disconnected. I increase the stimulus, and then I have a new community that forms, and I have my tree that has a new member. And so forth. I continue to increase my stimulus, and then I have almost all of them, for the exception of the one that is very far away, okay? Until I allow for all the system to be connected together. And so overall, with this tiny example, I can see how I can create some sort of hierarchical structure of what is the probability of things to be interacting together in a system like this one. In the same way, I'm creating the same type of tree that we saw in the brain. So this process that I've been telling you about with respect to increasing the stimulus and allowing the message to propagate in the space is called percolation. And this is something that is used in order to put fires out, for example. When you have a fire in a forest, what you have is a tree that is on fire, and then depending on the intensity of the fire and the proximity of the next tree is whether it will go to the next one. So if you want to put the fire out, you're not going to tackle all the trees, because you cannot tackle all the trees. What is it that you need to do? You need to observe and to see, is there a path that will create a huge fire? So you want to put the trees out to avoid of this fire to spread everywhere. This is the idea, to save most of the trees, to look at how these fires propagated in the space and creating this giant component. So this is the idea behind percolation, and this is the idea of how a message or something will be propagating in your space. So your trees, in our case, our points of intersection, in our road network, and what is propagating in the space. At the moment, it could be anything. We can think about the flows of individuals or just the probability of this happening. So if we do that for the UK, this is what happens. So what you're observing here is a set of clusters that appear as you increase this intensity, okay? So you allow for the distance to go further. You don't have all of them. If you only have in color the top 10, okay? You don't have all of them in there. So what you observe is that at the beginning you can recognize some of those different patterns. You can see that cities started forming. Then you can see that some regions that you might recognize started forming, and so forth. But the beauty about this idea of percolation is that as a physicist, we know how to study this type of systems. So you look at the transitions. So you have your clusters, and you want to see when all of a sudden it becomes very big. So when you have things that are merging together and becoming very big. So by studying the system using percolation, you're able to look at important transitions in the systems. Which regions appear? So what does it mean in my urban system doing things like that? So when I look at the country, so if I look at the UK, the first transition kind of tells me that the cores of the cities are forming. So the ones that have a good eye, this transition is around 200 meters. And it arises from London. Okay, so you have here these clusters, the blue and the red one, that all of a sudden merge. So this 190 meters, this 200 meters, what does it mean? Who has an insight into what is this number for this transition? You can win a fractal if you... Sorry? Distance of the bus stop. Actually, it's very interesting because in France, in order to construct the urbanized space, the way they do it is to see every 200 meters If there is another building, then you incorporate, then you construct the definition of the cities based on the continuous urbanization of 200 meters. But it's not the bus stop. What could it be? There is a hint here. You see? The north of London and the south of London. North of London in red. Why is it in red? Because it's the biggest cluster. And then you have the southern part of London in blue. The Thames, yes, is the bridge, okay? So the bridge that will be connecting these two spaces, okay? So we're talking about the road network here. Then we have this other type of regional divisions that happen. And you might think the chill turns there, but not quite, yes? So these are divisions. I don't know who are there any Brits here that look at this division that might say, I've seen this somewhere else? Where have you seen this division before? Election maps. Oh, such a beautiful answer, because I'm going to show you the election map in a minute. Beautiful answer. So this division, where have you seen this division? Have you seen it somewhere? So we will see in a minute where it comes from. Then we have other ones, other sort of divisions, okay? That might be, a vision into the future. We don't know. And overall, the thing to bear in mind is that this is the road network, okay? So all I have here is the road network. I don't have any other type of information. I have the road network, and I'm saying, can I spread the message into my space, and what will happen with that? And so when I take that one that I was asking you about, and I plot the income per capita, at the regional level, I have this type of pattern. So you have this division, this type of north-south divide that exists from, I will say from Roman times, maybe, but you could still see, you can see this division from very, very very old times. So here, in one of the maps, you have wealth, okay? You have income, okay? I'm plotting this income. This is 2001 income from the census. And then on the other hand, I only have the infrastructure. I don't have any other type of data. And I get similar patterns from one or the other one. So of course, what you can think is the way that the intensity of this infrastructure has taken place in one place and in another one. How the connection between spaces has happened in one place and in the other one. What is important of connecting these spaces? How do I see the structure of my space, and how I'm going to then invest in order to change how this looks like? So if I take all of these connections, and you remember that we built this tree according to these connections, looking at how the brain was structured, if I do that for this whole exercise of the percolation in the road network, I get something like that. So let us look at it the other way around. Let us imagine you have the whole of Britain, and then it splits into two: Scotland, England, and Wales, okay, according to this, to the connectivity of my space. Then as I go further, and I'm informed by the plot that I have on this inset of how I can follow these different transitions into my system. And then I continue doing that, and I see all the different type of regions emerging until I get into the level of my cities at the bottom. And one important thing to see, for example, is the northern powerhouse. So the northern powerhouse tried to connect all these cities that you have over here together with Newcastle, that is over there. So in order to reach Newcastle, you have to go, it's so far away into the system that within the road network, it wouldn't work. Okay, so you see how within the road network, it doesn't work when you're trying to integrate the region. So if I'm going to then take this tree and say, right, now I'm going to put I'm going to invest in this region, and I'm going to say that all the people are going to benefit, but who is really benefiting? How is this money really going to spread? How are the people? And of course, for something, in order to answer a question like this one, you will need to see how people are moving in your system. Okay? Who is benefiting? What is really the probability of interactions of these individuals? Yes? And actually, when the Northern Powerhouse was proposed, I think Newcastle decided to leave, and it didn't work, and then in the end, I think it came back. And so going into the answer about, well, before going into that, so what you see is that when you look, you have your country, you have your streets, and you have a new representation in order to understand your system in terms of this tree, in terms of the relationship between all the different cities that belong to regions and how these regions belong to the next one, and so forth. So if I'm going to put some sort of any type of intervention, who is going to benefit from this intervention if I do it in London, right? How far do I have to travel up the tree in order for this to spread? Is it going then to be only concentrated in London? So this is the way one can think about this system. And of course, here we build it with the street network, where you can think about building this tree with any other type of flow and any other type of connectivity between the different things. So going into the answer, going into voting kind of things. So when we came up with this tree and we look at that, we thought, okay, so we see how understanding the system in this way gives you some validation with respect to socio-demographic insight, as we saw in the previous slides. But given that now we're very much connected in the internet, are there also ideological divisions in the way, when we see this tree? And how are we going to measure ideology in something like that? So the way to look at it is voting patterns, okay? And this was very much inspired by Mike when he was looking at these maps. He's like, well, it does look at the way people are voting. And so the exercise that we did, so this was a very long time ago, it was 2015, we took the data from 2010 in order to explore how people were voting. So how to explore how people are voting, we use this tree. So you're going to assume that you're going to vote in a more similar way to the people that you're connected to in this tree. So if you belong to this mother cluster here, you're going to vote more similarly to the cities that are part of this mother cluster than this other one over here. Okay, so we did this experiment in order to see whether you will see a pattern that makes sense in the way people think in similar ways. So does it matter? Does our spatial embeddedness matter now that we all, spread news via the internet? And the result actually is that it does matter. So what you have here is a set of maps that depict the way people voted, our model, people voting according to other sort of things, for example, to qualifications, in this case, to occupations, to their age, and to their country of birth. And the one that was more similar was the one related to your connectivity in the space. So actually, you're not living in the space that you're living just by chance. You kind of choose to live because some sort of homophily principle. You can share things with the people that are around you, in the city that are around you. So far we show how through this exercise, we ended up with cores of cities, okay? Cores of cities. Not really the definition of city, the extent. So what is a city? So the whole issue when I started working in urban systems after studying ants was this idea of what is really a city? When we were studying ants, we had a colony. And that colony, you could put it in a petri dish. Okay, so here is my colony, here is my other colony, and I can make experiments and take ants out in order to see how things interact. But what do I do with my cities? What is my city? Because the city, what is the boundary of my city if people are going to go beyond these sort of things? So to understand this, we take this idea of how then the message will be spreading into space. And as the message spreads into space, the only other formula here, you will be creating all these networks that I showed you before in these pictures. So these networks in the transitions, they are fractals, okay? We saw that the cities are fractals. But you have different networks, and you're assuming that actually these cities are growing in a way that is self-similar. So I put a bit, I put on my electricity, and I see at that threshold what connectivity I get. And I look at all these different networks, and I measure the fractal dimension of these networks. And then I increase the threshold. I have other sort of networks, some connect. Of course, the first cities that will connect, you will see, is Liverpool and Manchester being so close together. So now there will be one cluster. I measure the fractal dimension of all of those ones, and I continue doing this. And as I do this, in this exercise of increasing and increasing and increasing how I allow my message to pass by, I observe that I reach a peak in the fractal dimension. And when I look into my space and I see what's happening in my urban systems of my networks when I'm doing this, I see that actually it corresponds to how cities are defined according to satellite data. So basically what I take here is a satellite data from the Landsat that classifies what is urbanized and what is not urbanized. So the pink colors correspond to urbanization and all the other ones to other things. So I look at my maps and I look at the boundaries of the cities that I created when I have the maximum of the fractal dimension, and that's the best correspondence that I get. So we have our definition of cities at the maximum of the fractal dimension, which is something very nice in order to go, which is very different, this definition, to the one that you will obtain with the boundaries, with the administrative boundaries in many cases. Okay, so to finalize, the takeaway message of all of this exercise is we're thinking about studying cities, taking examples from nature, right, in order to understand better things. But when we think about how nature has constructed all these type of things, really goes towards resilience. So all the patterns that you have observed, everything that you have seen so far, is the outcome of evolution. So you have evolution going on, and what is survived, it's for resilience, okay? When you look at the things that we constructed, we're not constructing these things to be sustainable. We're not constructing these things to be resilient. We're constructing them in an optimum way. So how can we then take all these examples of how we can construct our trees for each of the systems in our city, take it into account the Sustainable Development Goals? So you see, today what I show is a way to understand the connectivity between the elements when you think about the space and be able to go from one place to another one using our roads. You can think about it, well, Elsa, actually, what about, transport? We are beyond, what about trains and how this tree is going to change once we have our new set of transport that we didn't have in this previous one. But you think about the different layers. So this is just one layer transport that is connected to other things. We have the economic layer and we have all of these other layers. And once you move one of the layers, you're affecting the other one. How do you couple these layers? How do you couple them so that they're evolving towards a more sustainable space? Because everything that you're going to measure in your city, it's an emergent behavior of the interactions of the different layers. And to finalize, I want to show you one range of individuals with whom I have collaborated. So the important thing about this picture is that they all come from many different disciplines. So when looking at any type of complex systems, you cannot look at it from one perspective. So you cannot look at it from the perspective of the architect, you cannot look at it from the perspective of the anthropologist, you cannot look at it from the perspective of the physicist alone. You have to all come together, of the geographer, in order to be able to take all these different perspectives and all these different tools and put it together to try to understand better the system. And this is what complexity science is. It's to bring people together from different disciplines to understand something and to try to change the focus of this subject, to see how the interactions that maybe you were missing need to be taken into account, because once you switch something here, it will affect the other thing that is over there. And how is that happening? So this is what complexity science is about. Thank you.